Niels Sloane, who revolutionized experimental mathematics by creating the wonderful, wonderful tool, the OEIS, without which I will not know what to do. I'll maybe commit suicide. Yeah.
Alright, let me turn off the movie.
As usually, we're going to take Neil out for dinner, but let me know if you want to come right after the talk. Usually.
So it's been nearly 50 years since I started this project, and several people said it would be worthwhile putting on record, giving an overview of the whole project. So that's what I'm going to do. The title is the OEIS, the first 100 years. And I started this around 1964, and I'm going to give an overview. This is what it is. So I'll start off by describing the OEIS, and then I'll give a brief history, and I'll talk about the present version of the OEIS, and along the way I'll mention several new and interesting sequences, and then at the end I'll talk about our plans for the future, for the next 50 years. So this is the way the OEIS looks at the moment. The most important thing to remember is the URL, which is oeis.org, and this is the page you see when you go there. You can choose any one of 50 languages to look at the front page. And the idea is that you enter a sequence, you click search, and the database will report back what it knows about the sequence. And there are various nice features down here. There's a webcam. If you want to waste time, turn on the webcam. This is great fun. There's a link here for contributing new sequences and comments, and various other things. SuperSeeker, which I'll mention in a minute, and it's supported by the foundation. And so some facts about the OAIS. The idea is it's full of very accurate information about sequences. We stress accuracy above everything, and for each sequence we try to give formulas, definitions, references, links, programs in various languages like Maple, Mathematica, Paris, Magma, and so on for generating the sequence. And you can look at the sequence in many different ways, either as you can see a list. You can see if it's a two-dimensional array like Pascal's triangle, that you can click on a little button called table, and it'll transform it and show it to you as a two-dimensional array. Even though when we enter the triangles of numbers, we just scan them row by row. So of course we're basically dealing with cataloging one-dimensional sequences, but you can make a two-dimensional table or a triangle into a sequence by scanning it row by row or diagonal by diagonal. We get about 200 new entries or updates every day, which is really a lot of work. We need more help. We really need more editors to help with this process. I've been collecting articles that thank the OAIS, reference the OAIS, and now there are about 3,000 articles that reference the OAIS. And it's often called one of the best mathematical sites on the internet. And since 2010, it's been a wiki, so I don't have to do everything myself anymore. And the main uses, well, as you probably know, the main use is to find out if the sequence that you've looked at has been studied before by anybody else. You can say basically it's a way of avoiding having to think too hard about a sequence. You don't have to remember. You see something, well, you don't know, are these the Euler numbers or the Catalan numbers or whatever, you can just look them up. You don't have to think as hard. But most important, it'll tell you who else has worked on this sequence. And if it's not in the OAIS, well, that's very often a useful piece of information. It suggests that maybe this is a new problem that you're working on. One of the things that you really want to know about your sequence is how hard is it? Is it like the Catalan numbers, or is it like the 3x plus 1 problem? You know, there are people who believe that the question about whether the 3x plus 1 problem always converges to 1, it can't be proved under the standard axioms. That it's maybe true, but unprovable. And, well, you want to know, is your problem that hard, or is it somewhere in between? And that's one of the, and of course, even if it is that hard, can you relate it to a sequence that's already in the database? If your sequence is hard, but is related to the 3x plus 1 problem, for example, that's very interesting information. Another feature of the database is that people use it and contribute to it from all over the world. It's been called one of the most successful international collaborations. It's a source of fascinating research problems. That's one of the pleasures of being an editor, is that you see new sequences as they come in every day. Very often sequences that haven't been studied at all. Just someone has come across the sequence and they couldn't figure it out, so they send it into the OEIS. And if you're an editor, you get to see it. I'll show you in a minute a few sequences that have come in recent months that, as far as I know, no one has worked on. Lovely problems. Another feature of the OEIS is that it's led many people into mathematics. In the old days at Bell Labs, every year we used to have a day called Take Your Daughters to Work. And there were two of my colleagues who said that their daughters, I used to give a demonstration of the OEIS to these young ladies when they came in, and at least 2 of them have gone into mathematics, partly as a result of seeing the OEIS. And it's great fun, and another factor is that it's a great escape from the world. You know, the 4 standard ways of escaping from the world are sex, drugs, booze, games. Well, the OEIS is just as good, maybe better than these, because there are no side effects. So let me mention an appeal before I forget. If you see a sequence when you're in the library or on the internet, not necessarily your own, especially not your own, if you're browsing through a journal and you see a sequence, well, if it's not in the OEIS, please add it. And if it is in the OEIS, add a reference to it from that sequence to the article. And if it thanks the OAIS, then add it to the page on the wiki of works citing the OAIS. But especially add the reference. This is one of the most important features of the OEIS, to have lots and lots of references from sequences to all the different places where they're mentioned. And as I said, we need more editors, associate editors. There are no particular duties, just you get to look at the sequences as they come in and pick out interesting ones and do a bit of editing on them. So the history. So I began this back around 1964 when I was a grad student at Cornell working on perceptrons, what are now called neural networks. And I was studying a particular question that had to do with whether activity would die out in certain neural networks. And I was attacking this in a combinatorial way, looking at the data, doing experimental mathematics on this. And there were several sequences I came across. I needed to know how fast they would grow. And one of the simplest examples was if you have a rooted labeled tree, and you pick a node at random, how high is it above the root? And I worked out the first few terms, which normalized by n, go 1, 8, 78, 944. And with some difficulty, I worked out the 6th term. And I needed to know how fast this would grow in relation to the total number of nodes in all these trees, which is roughly n to the n. So the question is, how fast does this sequence grow when divided by n to the n? And if you plot it, it's really unclear. It grows like that, and you can't tell whether it's going to go like that, or the data wasn't adequate. So I started looking in various books. In those days, the best book on combinatorics was John Reardon's book, An Introduction to Combinatorial Analysis, which is still a great book. And he has a lot of sequences in that book. So I started collecting them. I wrote them down. I couldn't find this sequence, but I noticed that he had a lot of other sequences. So I started collecting them on index cards. And I looked in a few other books, Abramovitz and Stegen, a few other classical books that had lots of sequences. And I gradually built up a little stack of cards with interesting sequences, because I knew I was going to have lots of others to deal with. And I never did find this sequence, but I wrote to John Reardon, and he said, the most important thing, if you're counting things, is Polya's counting theory. And that's still very good advice. We ended up writing a joint paper about this particular class of sequences. And the answer is, there is a formula for this sequence. It's a sum of, a truncated sum of n to the k over factorial k. And once you have the formula, it's very easy to figure out how fast it grows with respect to n to the n. It grows like whatever root n, which is just what I wanted to know. So I collected these. After a while, I transferred them to punch cards. And various people said, gee, that's a great idea. I wonder why nobody has ever done this before. Richard Guy was very helpful and sent in a whole lot of sequences, and other people did. And after a while, I got a bit more serious about it. I went through all the books in the White Hall in the Cornell Math Library and collected a lot more. And I went to Brown University, which had a wonderful mathematics library, many classic books. And so, after a while, I found a publisher, Academic Press, kindly volunteered to publish it. And so the first book came out in 1973, which looks like this. It's still a nice book. I use it from time to time. And it has 2,372 sequences in it. And after that, a lot more sequences came in. People sent in manuscripts, typescripts, reprints, off-prints, postcards, ML letters, and so on. So after a year or two, I issued a supplement, and then another supplement. But then it just got out of hand. I figured I had about a cubic meter of correspondence waiting. And, well, it took a while. It was more than 20 years before the next book came out. Simon Plouffe at Montreal, UQAM in Montreal, offered to help. And so in 1995, we put out the second book, which we called the Encyclopedia of Integer Sequences. And then, of course, the floodgates opened. Many people sent in sequences. And so I waited until the number. That book had 5,400 sequences. I waited until it got to 10,000 sequences. I was updating the database myself all the time. After 10,000 sequences, I put it on the internet in 1996. And I called it the Online Encyclopedia of Integer Sequences. And it was launched with 10,000 sequences. The other thing I did in 1995 was, by then we had email. So I set up 2 servers. And they're still running. The address for the plain lookup is called sequences@oeis.org. If you don't have access to the internet, but you can send email to sequences@oeis.org and say lookup and enter the terms of the sequence separated by spaces, no commas. So here's an example, 2357, 13, 19, 23. And I mention this because this is a sequence that I'm still worried about. I put it on the board here. So here's the rule. It's a sequence that begins with 2, and then they're all primes. And when you get up to the 10th term, which is 29, you look at this and you notice that 31 plus 29 is 60, which is divisible by 10. 41 plus 31 is 72, which is divisible by 9. And that's the rule. So the rule is, you start with 2, and the nth term, you want to find a prime p with the property that p plus the previous term is divisible by n. And p should not be in the sequence already. So you take the smallest new prime, such that when you add it to the previous term, is divisible, the sum is divisible by n. So for instance, it begins 2, 3, 5. The next term, we want to prime p such that 5 plus p is divisible by 3. And 7 works because 5 plus 7 is 12, which is divisible by 3. So it goes like that. In sequence 134204, it was sent in by Leroy Quet. And the interesting thing about this sequence is that we don't know if it exists. It might not be well defined. Because if it should happen, that if here, for instance, if we've been going along and we get a 31, if the next time, if this had been the 30th term, it's 31, the next time we want a number, if this is 31, 31 does not, there's no prime p with the property that p plus 31 is divisible by 31. So if the prime, if this term, if the nth term divides n plus 1, then you're dead. So we don't know if this exists. And I don't know if this is a hard problem, and people have just not really looked at it hard enough, or is it a really hard problem? I don't know. We know that 800 million terms exist, but that's nothing. Right? We could die. So that's lookup. And that's the sequences at OAIS.org. The other server that also is still running is SuperSeeker. And this runs all kinds of programs. It takes your sequence, it does many 125 transformations of it, and looks them all up in the OEIS. If your sequence has a typo in it, if you've mistyped up to 3 characters, it'll give you all the matches for it. It uses agrep, and so on. So that was 1995. 1996, the OEIS went on the web. You could look up sequences and contribute sequences, propose sequences. The trouble is, I was the only one who had access to this database. It was on my homepage at AT&T. AT&T was very happy to have it there because it's a very useful thing. It was a good public service. It brought in a lot of traffic to the AT&T research website. In fact, when this got written up in /dot, it crashed the AT&T research website. And my boss was very happy, very proud of this. Look, we brought down the whole research website. But it was a lot of work, and it was clear that this was not a long-term solution. So in 2009, I did a couple of things. First of all, I set up a foundation called the OAIS Foundation, which is now a 501c3 public charity. And I transferred the intellectual property to the OEIS Foundation. And we rented space on a commercial hosting service that we were planning to put all of the OEIS on this hosting service, on a slice host. I think it's now called Rackspace. Slice host or Rackspace is the same. It's a commercial site. They do a very good job of hosting it. But when we tried to get the lookup service running, it wouldn't work. We were using the same software that Wikipedia uses, which is called the MediaWiki software. And the MediaWiki software is hopeless at looking up sequences. If you type in 2, 2, 3, 5, so and so on, using the MediaWiki software, it just failed to look up. So there was a period of about a year. We had it set up, but it wasn't working. And in the end, part of the software that the Wikipedia uses was written by someone, I think, in the Ukraine. It was a huge chunk of code, and we finally got in touch with him and asked him if he could modify it, and the answer was no. So in the end, Russ Cox, one of the trustees of the foundation, did a tremendous job. He rewrote everything in terms of SQLite, and now, thanks to his work, it actually runs. You can type in a sequence and it'll give you a response very quickly. He really saved the OEIS. I'd just about given up hope. there was a year's time between trying to start this and before it was actually working. But finally, on November 11th, 2010, we launched the official OEIS with 180,000 sequences. And my former colleague, David Applegate, is the webmaster, and he does a great job of keeping things running. So thanks to Russ Cox and David Applegate for this. Without them, the OEIS wouldn't exist in this form. So the present OEIS, as I said, it's owned by the OEIS Foundation, and the goals of the foundation, the charter, the bylaws, are to own the OEIS, to maintain it as a free service forever, and to collect money to do this. And I should mention that it would be remiss of me not to say that we're looking for donations to keep it running. It's a free service, it will always be free. At the moment we have 12 trustees, no one is paid, and it's a 501c3 public charity. And the way it works now, it's a wiki, a moderated wiki. You have to be a registered user to send in a new sequence or a correction or an update. We have a dozen editors-in-chief and 80 associate editors, and we need more, as I said. There are about 200 submissions every day. And if you're an editor, you see this kind of thing. At the top of the page, there'll be a link when you log in, so sequences awaiting review. And you'll see the stack of things waiting to be processed. Things with numbers like A211 are new sequences that have been sent in. And if you're an associate editor, you will click on it and see what it looks like, and you look it over and make suggestions, corrections, or you can just say, this looks fine, I approve it. Sequence with smaller numbers are existing sequences where people are sending in comments or updates or links or formulas or better programs and so on. And any particular day, we will have the stack will have several hundred of these. I'm not going to have too much time to mention other properties of the sequence database the way it is now, but one of the features that I like very much are puzzles. So here's a puzzle, 0000049 511055. What comes next? And the answer is you have to think like a Roman. The 55 is LV. You write the number in English and look for any Roman numeral that's embedded in it. There are a lot of nice puzzles in the sequence database. And people always ask me, does it ever happen that two sequences can agree for a long time but really be different? I once got a call from a certain testing service asking me this very question. And I said, yeah, well, yes, it can happen. Just because they agree for the first few terms doesn't mean they're the same sequence. And so here's an extreme example of that. If you look at the floor of 2n over log 2 and compare it with the ceiling of 2 over 2 to the 1 over n minus 1, these two sequences actually agree for quite a long time. You have to go to about 10 to the 18 terms before they differ for the first time. And then there are infinitely many differences. And the
Do they differ by 1?
Sorry?
Do they differ by 1 when they differ?
That's a good question. I don't think so, no. I think, no, there's no reason it would be 1. No. And, no. But of course you can work it out, continued fractions. And another question is, are there any theorems that exist because of the OEIS? Well, the 3,000 citations that I've collected show many examples of that. And one of the most famous is from 1988, which is a theorem about the result is a theorem about the tail in Gregory's series for pi over 4, which involves the Euler numbers, whose existence came about because Jonathan Borwein looked up the difference between two decimal expansions and noticed that this gave a sequence which was twice the Euler numbers. And after some work, there's a rather nice theorem in the monthly from 1989. And another thing I'm not going to have time really to mention are some unusual recurrences. The Fibonacci numbers are one of the biggest entries in the OAIS. That's sequence 45, many references, and a very simple, boring recurrence. But there are other recurrences which are not at all boring. And I'll just show you a couple of them. There's Recurrence recurrence, which goes like this. This is really my favorite sequence. And you can see it here. It begins 0, 1, 3, 6, 2, 7. And the rule is this. To get the nth term, you either add or subtract n from the previous term. So after the term number a of 1 is 1, then we add 2 to 1 and get 3. And we add 3 to 3 and get 6. The rule is you first try to subtract. So we try to subtract 3 from 3, but that would give us 0, and we've already seen a 0. So we can't do that. The term has to be a positive new number. So we have to add. So 3 plus 3 is 6. The fourth term, we try to subtract 4 from 6, and we can. That would give us 2, and we don't have a 2 already. So it's 2. So the rule is you subtract n from the previous term if that gives you a positive number you haven't seen before. Otherwise, you must add. So when you're adding, you do get repetitions. After the 7 here, we can subtract 6 from 7. Well, that would give us a positive number, but we've seen it. So we add it and we get 13. And so on. This was sent in by Bernardo Reckerman Santos from Colombia. Around 1992. Sequence 5132. And it is a very mysterious sequence. If you plot it, it goes up and down and up and down and up and down. And it's very hard to understand what's happening. And if you listen to it, which I will try to show you, and so on. You can listen to any one of the sequences, by the way. If you just click on listen, you get some kind of music out. This sequence, some numbers take quite a while to appear. 2 didn't appear until the 4th step, you may remember. 3 appeared at the 2nd step. 4 doesn't appear until 131 steps. 19 doesn't appear until about 100,000 steps. And the red numbers on that slide are the records. And if you look at the records of numbers that take a longer time to appear than any previous term, well, there aren't very many of them. And they appear at well-separated intervals. 19 doesn't appear for 100,000 terms. 61, 200,000, 879, 300,000. And then there was a gap. 1355 didn't appear for quite a long time. And we were beginning to think that it was never going to appear. But it did appear after 10 to the 12th steps. And then 2406 took a much longer time to appear. But it did appear. And after that, we had every term up to 852655. And that number has not appeared yet. And we have computed, with Ben Chaffin's help, he works for Intel, we have computed quite a lot of terms of this. We're now up to 10 to the 120 terms. And we still don't know if 852655 will appear or not. Another sequence that came in quite recently was sent in by Jan Ritzema van Eck in Utrecht. And I can do this one on the board because it's quite amusing. The first term is 0. Now, we haven't seen a 0 before, have we? So when you see a new term, the next term is 0.